Welcome back to the Inclusive Mathematics PD series. In Module 5, we will focus on mathematical modeling and the importance of including visual representations and metacognitive think-alouds when modeling concepts. By the end of this session, you should be able to explain the CRA model for math instruction. You will be able to describe the purpose and benefits of using visual representations of math concepts, as well as metacognitive think-alouds. Finally, you will have the opportunity to practice modeling with a metacognitive think-aloud using concrete or virtual manipulatives. Most of the modules in this series make great small group professional development opportunities that are broken into 6 short segments. While all modules can be completed alone, this module is particularly useful to complete along with a partner or in a small group. There will be multiple opportunities for you to practice. In the first module of the series, we described the different domains of math knowledge. As a quick review, let's go through a few examples to see if you can recognize which domain I am describing. Remember, the same content can be described through different domains lenses, so pay close attention to the wording. Okay, if I said recalling basic addition facts, which domain am I describing? Declarative, conceptual, procedural, or problem solving? Jot down your response or take a pause to discuss with a partner. Fluent recall of memorized information is part of the declarative knowledge and number sense domain. Next prompt. If students are adding 4 two-digit numbers using the standard US algorithm, which domain am I describing? Jot it down or discuss with a partner. This is mostly describing procedural knowledge because students would follow the steps for a standard algorithm. Of course, it is helpful to execute this procedural knowledge if the student also has a conceptual understanding of place value and some declarative math facts as well. Next prompt. If I asked a student to explain why the additive inverse cancels numbers out, so for example, combining -2 and +2 resulting in 0, which domain am I emphasizing? Jot it down or talk with a partner. Anytime we are asking a student to justify or explain their reasoning, we are emphasizing the conceptual knowledge domain. Next prompt. In this scenario, students are given a recipe for dinner that says it serves 3 to 4 people. Knowing that they have 8 people attending dinner, students are asked to adjust the recipe to update the ingredient quantities needed. Jot down your thoughts or discuss it with a partner. This is a prime example of problem solving. It will require the use of all 3 other domains of knowledge, though a calculator could be used to offload some of those lower order skills if needed. The great thing about this particular problem is that there isn't just one right answer. If the recipe serves 3 to 4, is doubling the recipe guaranteed to be enough? What if you wanted leftovers? What if some of the guests are children or babies? A task like this can generate some great mathematical discourse. Final prompt. If you ask students to use manipulatives to model why 100 can be thought of as a bundle of 10 tens, which we also call 100, which domain are we emphasizing? Pause to jot it down or discuss with a partner. This last example is a demonstration of conceptual understanding about our place value system. Manipulatives are generally used to support conceptual understanding while learning new procedures. That's why conceptual and procedural knowledge are the pillars in our structure. They should be built together. The remainder of this module will focus on the heart of math knowledge, conceptual understanding. Using visual representations is a great way to support conceptual understanding. You can't just show pictures though. The way they are presented matters, and it's often helpful to present them in more than one way. Here are 4 different ways you could present visual representations of concepts. Some of these fit better than others with different concepts. Some concepts can be presented in all of these ways, and offering multiple representations of the same concept can make your instruction more inclusive. For my example, we're going to look at the concept of identifying and categorizing quadrilaterals. Quadrilaterals are polygons with 4 sides. If you are unfamiliar with the definition of a polygon, it is any closed shape with all straight sides. If we just had students memorize that definition without really understanding what it means, they may have trouble generalizing and transferring that knowledge to novel situations. Instead, we need to take our time and use representations to help facilitate conceptual understanding. In this first conceptual model, I am showing you 4 different categories of quadrilaterals using a compare and contrast visual. If I look across all the rows, I can see that all quadrilaterals have 4 sides, 4 angles, and 4 vertices. I can see that only the square and the rhombus have 4 sides equal in length. Rectangles and squares must have all right angles, whereas a rhombus might have a right angle, but it might not. A trapezoid will never have more than one right angle, although that one depends on whether you use an inclusive or exclusive definition of a trapezoid. That was just one way to present the information. You may also want to present this concept in a transformational way. Start with a nonspecific quadrilateral. If I manipulate or transform that nonspecific quadrilateral so only one set of sides is parallel, it becomes a trapezoid. I could transform it again so both sets of sides are parallel, and it becomes a parallelogram. By doing this, opposite side lengths automatically become equal in length, which is another characteristic of a parallelogram. One way I could transform that parallelogram is to take it and shrink one set of sides so all sides are equal in length. This would make it a rhombus. Or I could take that same parallelogram and keep the side lengths the same, but just tilt it a little so all of the angles are right angles. This would turn my parallelogram into a rectangle. Then I could either take that rhombus and tilt it to make all right angles to get my most specific quadrilateral, the square, or I could take my rectangle and shorten the long sides so all sides are equal, and that would also make a square. This transformational model works really nicely for this concept. You could even have students make these shapes with manipulatives like pipe cleaners or wiki sticks for a hands-on approach to modeling transformation of quadrilaterals. This hierarchical model might look the same as the transformational model at first glance, but its purpose is a little different. The most general quadrilateral is at the top, and the most specific is at the bottom. Notice the direction of the arrows in this diagram. I can follow along any arrow path to see the relationship between these shapes. For example, this model shows that squares are also rectangles, kites, parallelograms, and rhombi. A square meets all the criteria for those quadrilateral shapes. However, looking at the direction of the arrows, I can see the inverse is not necessarily true. All squares are rhombi, but all rhombi aren't necessarily squares. This model is nice to show 3 distinct types of quadrilaterals: kites, parallelograms, and trapezoids. Kites are quadrilaterals with 2 pairs of equivalent adjacent sides. Both a rhombus and a square fit that definition too, so they are also kites. The square is the most specific example of a quadrilateral, and a square is also a rhombus, a rectangle, a parallelogram, and a kite. This diagram is also a good way to show how trapezoids are not in the main hierarchy of quadrilaterals because they only have one set of parallel sides. So a square is not a trapezoid because it has 2 pairs of parallel sides. Again, that trapezoid is a tricky one because there are really 2 different definitions of a trapezoid. The inclusive definition says it has at least 1 pair of parallel sides, while the exclusive definition says it has only 1 set of parallel sides. That's a big difference. Depending on which definition is used will impact its place on this diagram. The current visual you are looking at is using the exclusive definition, so it can only have 1 pair of parallel sides. That's why it's not in the same path as the parallelogram. A good practice in math is to use ample examples and non-examples. Sometimes students can learn about a concept by understanding what it is not, just as much as by understanding what it is. The model on this slide is for identifying quadrilaterals, not really for categorizing them, but you could use this technique for categorizing as well. On the left, students can see examples of closed polygons with 4 sides. On the right, students can see non-examples. I could point to specific non-examples and ask students why they are not quadrilaterals. Let's start with these. Why aren't these quadrilaterals? These aren't quadrilaterals because they have more or fewer than 4 sides, and quadrilaterals must have 4 sides. Why aren't these quadrilaterals? These shapes have curved sides, and quadrilaterals have to have only straight sides because they are polygons. How about this one? Why isn't this a quadrilateral? This one is not a closed shape, and quadrilaterals are polygons, so that means they are closed shapes, and they're a specific kind of polygon that has 4 straight sides. This is the idea behind asking students to look for an error in a math problem as a way of instructing them. Showing them the wrong way to solve it and asking them to correct it can be a valuable process to build conceptual understanding. So which method is best? There really is no best model. You should always be using multiple representations of the same concepts to help build conceptual understanding. It doesn't mean every method is useful for every concept, nor does it mean that these are the only 4 ways of representing a concept. Sometimes you need to think outside the box and allow your students to help you build these representations too. You do not need to give all of these representations within the same lesson. This is where assessment of your students and your professional judgment comes into play. When discussing conceptual knowledge, we have to also address the CRA model for instruction. Math can be pretty abstract. When we write math, we have symbols that stand for some concept. The CRA framework for instruction can help students translate from the concrete to the abstract. The models I just showed you were all visual. For students with dyscalculia who may have visuospatial deficits, you may need to begin with something more tangible. That's why I suggested using pipe cleaners or wiki sticks as a concrete manipulative for the transformational model. The C in the CRA stands for concrete. Concrete objects are manipulatives like base 10 blocks, fraction tiles, counters, and play money. These are things that students can physically touch and manipulate to solve problems. Using concrete manipulatives aren't a fluent way to solve problems, though. They can help build conceptual and even procedural knowledge, but as the students become more fluent with the manipulatives, you can move to drawing representations of those manipulatives. Instead of physically moving the manipulatives to show regrouping, I could use circles, arrows, and lines to represent those actions. It's representational because I'm not physically manipulating anything, and I'm using some symbols to represent those physical items. Showing representations like this is often a great instructional scaffold. Numbers and symbols are abstract. Eventually, we want our students solving problems using our abstract number and symbol system because it's efficient and it's the language of math. We can still scaffold abstract models, though. Look closely at the representational model on the top right and the abstract model on the bottom right. I could use an alternative algorithm like this expanded form method of addition to help translate from the representational stage to the abstract stage. Eventually, as students understand the concepts of place value and regrouping with regards to addition, they can successfully utilize the traditional abstract model. Here are some considerations for using concrete manipulatives in your classroom. First, you need to match the manipulatives to the task and concept you're trying to teach. You probably wouldn't want to use base 10 blocks to teach geometry. In your lesson planning process, make sure you plan and practice your verbal explanations of how to use manipulatives. You should be using the explicit instruction model when you introduce a manipulative. Model first with a clear think aloud, and then let students practice with your support before you have them apply manipulatives independently. You have to explicitly plan how to show students the connection between the manipulatives and the paper-pencil representational or abstract task. Don't just use manipulatives one day and the next day try it on paper without helping the students make that connection. Allow your students to verbally explain their actions while using the manipulatives. This is a great time to allow your students to be the experts. Have them teach someone else how to use them. Finally, make sure you consider individual needs. A student with a physical impairment or a visual impairment may not be able to use the same manipulatives as their peers. Manipulatives also come with logistical considerations. Some secondary teachers think manipulatives are only for elementary students. Secondary math is the most abstract, so manipulatives can be a great tool. Oftentimes in secondary education, virtual manipulatives are more common, given the time and space constraints of classrooms, where students travel from room to room. Don't forget, you need to teach students how to use the manipulatives. You can't just give it to the students and say, "Here you go, use them." Different manipulatives will be appropriate in different situations. They can add some needed engagement and variety to your lessons. The last logistical consideration I want to mention is to have an organized system for distributing manipulatives. Some teachers don't use manipulatives because they are a burden to manage with large groups of students. But if you already have materials sorted in individual baggies, or if you have manipulatives in buckets at each table, it may help the process go more smoothly. Here's one final consideration. As we start leveraging more and more technology in the classroom, we may find ourselves using some virtual manipulatives. Where do you think these fit in the CRA model? They aren't 3D objects you can physically hold, but unlike most representatives, which are drawings, you can manipulate them. If you couldn't decide which one they fit best in, don't worry, you are not alone. Though there is more and more research on virtual manipulatives, the research base is in its relative infancy compared to research on concrete manipulatives. Some researchers categorize them as concrete, while others say they are representational. Others take a more neutral approach and call them semi-concrete. For some students, these could take the place of physically holding concrete objects. But for some students, use of virtual manipulatives may come in between the C and the R as a way to phase them into representations. Generally, you may be able to skip the fully concrete for older students and move right into virtual manipulatives. But more research still needs to be conducted in this area. One of my favorite places for free virtual manipulatives is through the Math Learning Center, which is part of the Bridges Math program. They have all kinds of virtual manipulatives that can be used on the web or on mobile devices if you download their free apps. You may want to head to this website and bookmark it for an activity shortly. Manipulatives, virtual manipulatives, or representations of those manipulatives can be used to support conceptual knowledge. This can be done through student exploration and inquiry methods. But for students who are struggling in mathematics, some explicit modeling is an effective approach to building conceptual knowledge. The key is, when modeling, you need to include a metacognitive think aloud, meaning you are verbally modeling all of the things you are thinking while you are using the manipulatives or making drawings. This is easier said than done, because it can sometimes feel unnatural to speak your thoughts out loud. Let me model for you what I might use for a metacognitive think aloud. Let's say I am modeling a subtraction problem that would require regrouping if I use the standard US algorithm. Let's say we have already taught some partial difference methods and we are ready to teach the standard algorithm for the first time. I need to think about what kinds of manipulatives I want to use. I think base 10 blocks would be a good choice. For this example, I am going to use the representational model and talk you through my example of modeling two-digit subtraction with regrouping using a metacognitive think aloud. In guided practice, I may have some students using concrete manipulatives and using some representations, depending on their readiness. In guided practice, I may have some students using concrete and some using representations, depending on their readiness. Within my modeling, I also want to give some opportunities to respond for my students. I'll be modeling the new content, and they'll be using some think, pair, shares, or choral responses for some of the review content. Today we're going to do some more practicing with subtraction, but our numbers today are going to be a little bit trickier. So we're going to use some representations of base 10 blocks to do this problem. I put a little reminder in the upper left-hand corner there that we can draw our flats, our rods, and our units pretty easily with simple drawings. Just like any simple subtraction problem, we usually like to model our first number, model that minuend, and then we take away our second number, the subtrahend. So let's go ahead and follow the same process we've been using. So first, let's model the minuend, the first number, 42. Turn to your neighbor and remind them how many tens and how many ones are in this number. Okay, let's do these answers out loud. How many 10s, everyone? 4. Very good. Count by 10s with me as we draw our base 10 blocks. 10, 20, 30, 40. Great. Okay, everyone all together. How many 1s in 42? Great. 2 1s. Count with me. 1, 2. Give me a thumbs up if you think we've correctly modeled our minuend, 42. Great. Now, we're going to subtract, which I can think of as take away, my subtrahend, my second number. So I need to take away 18. Turn to your neighbor and tell them how many 10s and how many 1s are in 18. Okay, all together, how many 10s, everyone? 1. Great. How many 1s? 8. Great. Okay, so to take away, we usually just draw representations by crossing them out. I'm going to use red to make it easy to see. All right, we're going to take away 1 10. There it is. I've crossed out one of my 10s. And we're going to take away 8 1s. Count with me. 1, 2. Uh-oh. I see a little problem here. I have run out of 1s to take away. Does this mean we can't solve this problem? Turn to your neighbor and brainstorm a few ideas of what we could do now. Does anyone have any ideas they could share out? Oh, someone's saying that we might be able to exchange one of our 10s for 10 units. That's called regrouping. Great idea. Let's try that. I'm going to do that in a different color. I'm going to use my purple marker to do this. All right, so I'm going to take one of these 10s and exchange it into 10 1s. When I draw my 1s, I like to draw them in a nice pattern so they're really quick and easy to count. So I'm drawing mine as if they were in a 10s frame, those 2 rows of 5 like that. So I've taken and regrouped one of my 10s and I've made 10 1s. Great. Let's try to do this problem again. So if I want to take away 18, we already took away 1 10. Now let's try to take away 8 1s. It looks like there's enough now. So here we go. 1, 2, count with me. 3, 4, 5, 6, 7, 8. Very good. I've taken away 1 10 and 8 1s. All that's left is seeing what our difference is, what's remaining. Go ahead and try to count on your own and then tell your neighbor what you got. Great. All right, all together, how many 10s do we have left? I see 1, 2 10s. Very good, everyone. How many 1s all together? Good, 4 1s. On your whiteboards, go ahead and write down our difference of this subtraction problem. If I have 2 10s and 4 1s, what number is that? Hold it up so I can see. Very good. We all got 24. Okay, hopefully you get the idea. Modeling while thinking out loud can be a little tricky. You need to practice to do it well and find the appropriate opportunities for students to respond and engage with the content. Okay, it's your turn to try a metacognitive think aloud with a partner. Choose one of the 2 problems from below, and then choose a manipulative type to either use concretely for your modeling or that you could draw representationally. You may also want to try virtual manipulatives from the Math Learning Center. Take turns being the teacher and the student. Teachers, don't forget to verbalize your thinking for new content and prompt for responses with the review content. Let's extend your knowledge even more on your own. If you haven't gone there already, head to the Math Learning Center website to access their virtual manipulatives. Try them out and notice how they differ from static representations of manipulatives. Share out with your colleagues.